Dear students, we continue discussion of chronic pending model, in which we have discussed about the motion of an electron in a periodic potential, and using this model we have discussed how energy bands are created, and we have derived a condition for the chronic pending model also. Okay. So, in this model I forgot to mention what is the number of orbitals in a band. Okay. So, here k can take value, the allowed values of ks are 0, plus or minus 2 pi by L, and plus or minus 4 pi by L, etc., up to plus or minus n pi by L. Okay. And here I have taken n is an even integer, which represents the number of primitive cells of lattice constant A. Okay. Now, how much distinct values of k's are allowed. Okay. So, this we have to determine. So, that will give you the number of orbitals in a band. Okay. And even though k can take this many values, in the first Brillouin zone we have some limitations. Okay. So, this series actually cut off at n pi by L equal to pi by A, because that is the boundary of first Brillouin zone. Okay. It is plus or minus pi by A. Okay. Now, so there will be two values, one is minus n pi by L equal to minus pi by A, and another boundary which is n pi by L equal to pi by A. Okay. These are two boundaries, but we cannot take this as an independent value. I mean the value minus n pi by L equal to minus pi by A. This is not a distinct value. Instead, it is connected to pi by A by some reciprocal lattice vector. Okay. And we can always have mapping from other Brillouin zone to motion in the first Brillouin zone. Okay. And while discussing the vibration of lattice, we have seen k dash can be written as k plus 2 pi by A. Okay. And so, this is a reciprocal lattice vector. So, this is cannot be counted as a distinct value. So, the total number of points is exactly n. Okay. So, the total number of bands. Okay. So, here even though k can take plus or minus value, the minus sign value is not counted here. So, there are how many numbers of orbitals are there? You can see it is having n number of orbitals are possible in the band. Okay, avoiding the minus n pi by L value, and the series has a cutoff when n pi by L equal to pi by A. Okay. So, that means what is the number of bands in number of orbitals in a band? So, if you have n number of primitive cells of the lattice constant A, okay, that means in a linear crystal which is constructed of an even number of primitive cell, n number of primitive cells of lattice constant A, the number of orbitals in the band is given by n. That means each primitive cell contribute exactly one independent value of k to each energy band. So, each energy band will be having several number of orbitals, and these orbitals are determined by the how many primitive cells are there in the lattice. Okay. So, each primitive cell contribute exactly one independent value of k. Okay. Next, we move on to the discussion of band gap. Okay. And while discussing the chronic pending model, we have described how energy bands are formed in a material. Okay. And you have seen different kinds of materials depending upon the energy levels or energy bands. Okay. Basically energy bands, not the energy level. Okay. And here we have we are going to discuss about the band gap, which is the energy gap between the allowed energy bands in the material. Okay. So, there will be some gaps in the energy band so that I mean the region in the energy band which are forbidden, those are called energy gaps. Okay, and so in this video we'll be looking at how to define the band gap. Okay, it's an important parameter which is taken into account when we discuss the carrier concentration and nature of the material, etc. Okay. Now so the band gap, energy band gap or band gap is the energy difference between the conduction band edge and the valence band edge. Okay, so this is the definition of band gap. What do you mean by conduction band edge? Okay, that means in the material you will be having the conduction band. Okay, in the case space, if you plot, suppose you take this diagram. Okay, so this is some conduction band which is having some population of electrons here. Okay, and it has a minimum at some point, and that minimum of the conduction band is called the conduction band edge, and below that you will be having a valence band. Suppose for in this case, so the valence band will be having a higher value of highest value at some point, which is called a valence band edge. Okay, and so this difference, the difference between energy difference between conduction band edge and the valence band edge, okay, or the energy difference between the minimum of conduction band and the maximum of valence band is called a band gap. Okay, and here I have shown different types of energy bands. Okay, first one refers to an insulator, and the second one can be a metal or semi metal. We have discussed this figure before, and the third one is a metal because electron concentration, because there are some free electron in the conduction band. Okay, and this could be a semi metal or a semi conductor, could be semiconductor also. Okay, now the intrinsic carrier concentration or the in a material will be having the charge carriers, or which is responsible for the conduction. Okay, and the number of such charge carriers, or those who are responsible for the conduction, which is called the carrier. Okay, and the intrinsic carrier concentration is actually controlled by a parameter which is Eg by kBt, where Eg is the band gap and kB is the Boltzmann constant and T is the temperature. Okay, and if this number is very large, what do you mean by that? It means that the band gap is very large. Okay, band gap is very large, and so in this case the carrier concentration will be very low. Okay, basically the charge carriers in the conduction band will be very low, so that will give you material which is insulator. Okay, and depending upon the value of Eg, the band gap, we can categorize the material into different ways. Okay, different names basically, and if Eg is of the order of 1 electron volt, okay, which is of the order of 1 electron volt, then you can call it as a semiconductor, and if Eg is of the order of 5 electron volt, it's an insulator, and in the case of metals is very Eg is very small, or it can be negligible also. Okay, so it's an important parameter to determine the nature of the material. Okay, so here I have shown in this graph I have shown the conduction electron concentration. Okay, so at for different materials I have shown here. So you can see for metals the carrier concentration is very large, it is of the order of 10 raised to 23, and for semiconductor it ranges from 10 raised to 22 to 10 raised to 17, and for a semiconductor like germanium, silicon, etc., it varies from 10 raised to 17 to 10 raised to 13. So this is basically the difference between semiconductor and semi metals. We can talk in terms of the carrier concentration. Carrier concentration for semi metals is bit large than the carrier concentration for a semiconductor. Okay. Now there are different kinds of band gaps in the material, mainly two types. Okay. One is the direct band gap materials and the indirect band gap material. Okay. So we are mainly talking about the insulators, which is having direct band gap. Okay. That means so you have a material and the minimum of the conduction band edge and the maximum of the valence band edge, valence band. Basically the conduction band edge and the valence band edge occurs at the same value of k. Okay. So the wave number is same for the minimum the conduction band edge as well as the valence band edge. Okay. Now in the case of indirect band gap, there is a so these are separated. The conduction band edge and the valence band edge are separated in the k space. Okay, separated in the sense so this conduction band edge occurs at some point and the valence band edge occurs at some point. Okay, at some point in the k space. So these are widely separated in the k space. Okay. So in this this kind of material is called or insulators are called indirect band gap insulators. Okay. Now so this nature of the band gap in the material are determined by the optical absorption process. Okay. So you know നമ്മളൊരു ലൈറ്റ് ഈ മെറ്റീരിയലിലേക്ക് ഷൈൻ ചെയ്യുകയാണെന്നെങ്കിൽ the electrons in the valence band absorb the energy and it get excited to the conduction band. Okay. So leaving behind a hole. Okay. And this process taking place at a same value of k. Okay. Because it takes a hole with to the conduction band edge with no significant change in the wave number k. Okay. So such materials are called direct band gap material, and it is also called, this process is also called the direct absorption process. Okay. So whatever you are given, energy given is h cross omega. So this is the incident energy and the electron will absorb. So this energy this absorption process happens when this energy is equal to Eg, the band gap. Okay. So you can see the process absorption process here. It is the absorption coefficient on the y axis, and along the x axis you have photon energy. Okay. So up to this h cross omega g energy there is no absorption. So when you shine the light, if it does not have any energy which is h cross omega, basically Eg ഇൻസിഡൻ്റ് ചെയ്യുന്ന ഫോട്ടോണിന് ഇ ജി എനർജി ഇല്ല എങ്കിൽ അത് അബ്സോർബ് ചെയ്യുന്നില്ല. വെൻ ഇറ്റ് ഹാവിങ് എനർജി ഇ ജി ഓർ ഗ്രേറ്റർ ദാൻ ഇ ജി, സോ this much amount of energy will be absorbed. Okay. Absorption coefficient, there is a sharp transition, and the onset of absorption, direct absorption, will give you the energy band gap. Okay. So this is also a method to determine the energy band gap. Band gap എത്രയാണെന്ന് കാൽക്കുലേറ്റ് ചെയ്യാൻ വേണ്ടിയിട്ട് ഈ അബ്സോർപ്ഷൻ പ്രോസസ്സ് നമുക്ക് യൂസ് ചെയ്യാം. സോ ഓൾ യു ഹാവ് ടു ഡു ഈസ് യു ഷൈൻ ദ മെറ്റീരിയൽ വിത്ത് photons and calculate the absorption coefficient and a plot a graph between incident photon energy and absorption coefficient, and you look at the onset of absorption process that will give you, so this much energy will give you the band gap energy. Okay. Now what happens in indirect band gap? So indirect band gap, even if you supply energy, the absorption process here it is mediated by not only by photon but also by a phonon. Okay. Because of the energy conservation in this process. Okay. Suppose you shine the material with some energy h cross omega. Okay. It will not go to this conduction band edge directly. So there will be for the conservation of momentum and energy relations are given here. So h cross omega should be equal to Eg. Eg is basically this much energy and plus h cross omega. So this is the energy of the phonon. Okay. So this is required for the conservation of energy. Okay, so so this process creates a hole, a free hole and a free electron and a phonon also. Okay, so this process is mediated by phonon as well as photons. Okay, and omega is the frequency of the phonon. Okay, and this will give you the conservation of momentum. Okay, so this is the momentum of the photon, and there is a critical value which is called Kc, and K is basically the wave number of the phonon. Okay, now in this case the absorption process, if you look at the absorption process, the onset of indirect transition happens at Eg plus h cross omega. Okay, it does not starts at h cross Eg. Okay, the onset എന്ന് പറയുന്നത് Eg അല്ല, Eg plus this much energy needed h cross omega. So this is basically the phonon energy. Okay, onset start ചെയ്യുന്നത് ഒരു ഷാർപ്പായിട്ടുള്ളൊരു ട്രാൻസിഷൻ അല്ല. അപ്പം ഇതിൻ്റെ ഒരു നേച്ചർ അബ്സോർപ്ഷൻ ഡയഗ്രാം വരയ്ക്കുന്ന സമയത്ത് തന്നെ നമുക്കത് ഡയറക്റ്റ് ബാൻഡ് ഗ്യാപ്പ് ആണോ ഇൻഡയറക്റ്റ് ബാൻഡ് ഗ്യാപ്പ് ആണോ എന്ന് നമുക്ക് മനസ്സിലാവും. ഓക്കെ, സോ ഇവിടെ എക്സ്ട്രാപോളേറ്റ് ചെയ്തിട്ട് നമുക്കിതിൻ്റെ ഡയറക്റ്റ് ഓൺസെറ്റ് ഓഫ് ഡയറക്റ്റ് ട്രാൻസിഷൻ കണ്ടുപിടിക്കാം. ഓക്കെ, അതിന് ഈ വെർട്ടിക്കൽ ട്രാൻസിഷൻ എന്ന് പറയാം. ഓക്കെ, ഇറ്റ്സ് എ ത്രെഷോൾഡ് ഫോർ ദ ക്രിയേഷൻ ഓഫ് ഫ്രീ ഇലക്ട്രോൺ ആൻഡ് എ ഫ്രീ ഹോൾ വിത്ത് നോ ഫൊനോൺസ് ഇൻവോൾവ്. ഓക്കെ, ഫൊനോൺസ് ഇൻവോൾവ് ചെയ്യാതെ, കാര്യം ഈ പ്രോസസ്സ് ഇവിടുന്ന് ഇങ്ങോട്ടുള്ള പ്രോസസ്സ് എന്ന് പറയുന്നത് ഫൊനോൺസ് ഇല്ലാണ്ട് ഇവിടെ എത്തുന്ന പ്രോസസ്സാണ്. ഓക്കെ, സോ ദാറ്റ് ഈസ് കോൾഡ് എ വെർട്ടിക്കൽ ട്രാൻസിഷൻ. ഓക്കെ, so these are basically the direct and indirect band gap energy, indirect band gap materials or insulators. Okay, so this will be asked as a short question. So the important figures are given here. One is this figure, the energy level diagram in the case space, energy band diagram in the case space, and the absorption diagrams is important for discussion of the direct band gap and indirect band gap materials. Now here I have shown an experimental data of indium antimonide, and so here I have plotted here shown the absorption coefficient for indium antimonide as a function of the incident photon energy, and you can see from the nature of the graph, ഈ ഗ്രാഫ് കണ്ടു കഴിഞ്ഞാൽ ഇനി നമുക്ക് മനസ്സിലാവും there is a sharp transition at some point. സോ ഈ ഷാർപ്പ് ട്രാൻസിഷൻ ഉള്ളതുകൊണ്ട് ഇറ്റ്സ് എ ഡയറക്റ്റ് ബാൻഡ് ഗ്യാപ്പ് മെറ്റീരിയൽ ആണെന്ന് പറയാം. ഓക്കെ, അതൊരു ഇൻഡയറക്റ്റ് ബാൻഡ് ഗ്യാപ്പ് ആയിരുന്നെങ്കിൽ നമുക്ക് കിട്ടുന്ന ഡയഗ്രാം എന്നുള്ളത് സംതിങ് ലൈക്ക് ദിസ്. ഓക്കെ, സോ ദർ വിൽ ബി സം പോർഷൻ വിച്ച് ഈസ് മീഡിയേറ്റഡ് ബൈ phonon also. Okay, so since that is not present, the absorption spectrum, the absorption coefficient of indium antimonide shows a direct transition or direct absorption process. So it's a direct band gap material. Okay, so we can use the optical absorption process for the determination of nature of band gap. Okay, so ഈ ഒരു എക്സ്പെരിമെൻ്റൽ ഒപ്റ്റിക്കൽ അബ്സോർപ്ഷൻ എന്നുള്ള എക്സ്പെരിമെൻ്റ് വെച്ചിട്ട് ഒരു മെറ്റീരിയൽ ഡയറക്റ്റ് ബാൻഡ് ഗ്യാപ്പ് മെറ്റീരിയൽ ആണോ ഇൻഡയറക്റ്റ് ബാൻഡ് ഗ്യാപ്പ് മെറ്റീരിയൽ ആണോ എന്ന് നമുക്ക് ഡിറ്റർമിൻ ചെയ്യാവുന്നതാണ്. Hope you understood the video. Thank you.